Start the recording. Please accept it. That's great. And welcome everyone to the California Water Data Consortium's May Data for Lunch. I'm Tara Moran, CEO of the California Water Data Consortium, and very excited to be here with all of you today. And for today's topic, we have a presentation for today entitled Machine Learning for Rivers, How Data Science Can Inform Water Management in California. And just to give you a quick overview of our time together, we'll start today with a little bit of information about the consortium. We'll then have an introduction to our speakers, which will be given by Nick Martirano, who is a steering committee co-chair with the consortium and director of the California Water Quality Monitoring Council. From there, we'll have an approximately 30-minute presentation, followed by Q&A, which Nick and I will co-moderate. And then additionally, for those of you who are particularly interested in the topic and have some additional time, our speakers have graciously agreed to stay on this Zoom as late as 1:30 p.m. So we can continue our discussion and have some less formal discussion around the topic area. So for those of you who may not be familiar with the consortium or are joining us for the first time, just a little bit of background on who we are. The consortium was founded in 2019 to support implementation of the Open and Transparent Water Data Act, sometimes referred to as AB 1755. And as you all well know, data can and should be at the heart of well-informed water management, both here in California and beyond. And that really is the vision of the consortium, which in partnership with state agencies, NGOs, private sector, community-based organizations, academia, and many others, we support the development and improved accessibility to high quality, trusted water data to support better outcomes for everyone living and working in California. And so as part of our work, we host what we call our Data for Lunch series with the goal of both providing a venue for learning about new and innovative water-related data and methods, sharing learning on water-related data topics, and then really just a chance to connect and learn from one another. And so as I mentioned earlier, I'm very excited about today's presentations. We're going to learn a lot from our speakers. But one thing I wanted to flag is that earlier this year, the Data Consortium released a report entitled Putting Data to Work. And we'll go ahead and drop a link into the chat. But as the basis for that report, we talked with individuals involved in water management across geographies and sectors across California to really learn and hear about how gaps in water data are impacting their decision-making and water management outcomes, and then to learn more about where existing data gaps are. And importantly, one of the data gaps that came up time and time again in our interviews was stream gauge data. And that's because, as we'll learn here today, stream gauges only cover about 10% of rivers here in California, and 70% of watersheds still have no active gauges or history of gauges in the state. And this is really critical information. Stream gauges provide this absolutely critical data for answering questions like how much water should naturally be flowing in streams and how much water is actually flowing in the stream at present. And so thanks to the good work that Kirk and Laura and others are doing, we're now in a position to really leverage machine learning to begin answering these questions in ways that don't replace measured stream data, but certainly supplement it and provide us with an opportunity to think strategically about how and where we place those gauges. And so with that in mind, I'm going to hand things over to Nick Martirano, who's going to introduce our two fantastic speakers.
Thanks, Tara. Excited to be here and to introduce our esteemed speakers. I'd like to introduce them today. First is Kirk Klausmeyer, Director of Data Science for the Nature Conservancy's California program. In his 18 years at the Conservancy, Kirk has made significant contributions to California's environmental conservation efforts. He has built a machine learning data pipeline to predict natural flows in all the rivers in the state, mapped groundwater-dependent ecosystems to inform groundwater management, and analyzed satellite and drone data to track habitat for migratory birds. Our second speaker is Laura Reed. She's a water resources engineer with 10 years of experience in hydrologic modeling, forecasting, and decision tools. At Upstream Tech, she is head of product strategy for HydroForecast, where she leads the technical direction and strategy based on industry and customer feedback. If during the talk you have questions as they are speaking, please feel free to put those into the Zoom chat. Tara and I will be collecting those questions for the Q&A at the end of the presentation. And with that, I'll turn it over to Kirk.
Great, thank you so much. Welcome everyone to Data for Lunch. I hope you have some actual lunch because we're not serving anything other than data today. I'm going to share my screen and pull up my presentation. Okay, so as Laura and Nick mentioned, we're talking about machine learning today. And this is certainly a hot topic right now. It's exciting when your area of expertise is all of a sudden blows up in the general media. ChatGPT is taking the world by storm. I actually use it daily to help me with coding and to answer some of life's biggest questions. So I encourage you to explore some of these interesting tools like ChatGPT. And Dolly, generative AI, all this stuff is really exciting. And at the Nature Conservancy, we try to build on the innovation happening throughout the world in technology, and how do we apply that to conservation, to water management, to just better filling in data gaps where we have them. And as Tara mentioned, rivers is one of the biggest areas we have data gaps. So how do we leverage sort of this energy, this innovation that's happening in data science right now for conservation, for river management? So I'm going to talk to you a little bit about the work we've done, and then Laura is going to talk more about a similar project and some of the advances we're looking forward towards in the future. So to start off the problem, as Tara mentioned, we have stream gauges in California. And on the left side map, we've got a recent report put out by the state of California that indicated there's quite a few blue rivers here. Those rivers have a stream gauge, an active stream gauge that's measuring flow and reporting data in near real time. So if you look at the map, you're like, that's pretty good. I see some blue rivers. The light blue rivers are almost well gauged. They're, maybe they're not reporting flow, but they do report stage, or maybe they don't report in real time, but they delay the data for 9 to 12 months, something like that. The red rivers indicate places where there was once a stream gauge, but it is now inactive. And so that's not great. We don't know what's going on there now, but we have an idea what happened there in the past. But then when you look at all of the gray rivers, this is kind of a lot of light gray rivers throughout the state. Those have never been gauged. And that's the biggest data gap we have here is there's a lot of rivers throughout the state that have never had a stream gauge. And when we look at the watershed scale, the map on the right, you can see that this actually covers a significant area of the state. These watersheds, if they're sort of that solid red color, have no gauge history and no gauge now. And that is about 70% of the watersheds, even after you eliminate watersheds that don't have streams or are mostly water. So that's the problem. We have some data, pretty good data in certain locations, and then a lot of places without data. And this type of problem is really well suited to machine learning. You can take the information where you have it, build a model that takes information about those watersheds and about the rainfall and temperature, and then predict what the flow could be or should be or was historically in those places without gauges. So we have applied this concept, machine learning, to this problem and have some really good successes. Before we get into the actual data, I just wanted to do a quick tutorial. What is machine learning? And we're going to jump out of the world of rivers and into the world of home prices. And just as an example of sort of how does this work? What are we talking about? I want to demystify this machine learning a little bit. It's not all just sci-fi. computer brains. It's actually pretty basic statistics, but the power of computers really make this work much better. So in the world of housing, we can build these hedonic price models. And what that basically does is it can take information on homes that have been sold. So that's the data we have now. What was the selling price for the home? Characteristics about that home, its location, the number of bedrooms, et cetera. And then we could predict for where we don't have data about a home sale, like a new home going up for sale, how much should it be priced for? Or is the current price a good deal? So here is an example of what the machine learning does sort of in the back end. We take training data, which is, you always have to have training data in order to do machine learning. You take a database of historical home sales, and that could include characteristics about the home and the sales price. And then you feed that into these machine learning tools. One of the tools that works quite well is called random forest. And as you can imagine, a forest is built out of trees. So what this tool does is it starts to build trees based on the training data. And it looks at the data and it says, okay, I see some characteristics and then some sales prices. I'm going to start splitting the data into these different groups and trying to keep the sales price in clumps, basically try to segment the data. And you might sort the data by sales price and then look for all the low priced homes, what's a characteristic of them, and all the high priced homes, what's a characteristic of that. And so for those homes, so here in this, the computer does this for you, and it says, okay, well, look, affluent areas, that's a big differentiator on home prices. If it's located in an affluent area, yes, then most of the homes tend to be higher prices. And if it's not in an affluent area, most of the homes have lower values. And then you can keep splitting the data. Once you do this split, take the remaining data and you say, okay, of the homes in affluent areas, what bedrooms, number of bedrooms is an important factor. And most of the higher priced homes have more than 2 bedrooms. Most of the lower priced homes within this subset have 2 or less bedrooms. And then you start to split out the data into all these groups. And then in the end, you take the average price of all the homes that meet those conditions. And in this case, this is obviously not in California because the average price for the affluent large homes is $420,000. And for the smaller homes in affluent areas, it's $280,000. And again, you break this out based on other characteristics as well. Now that'd be great. You could use that as your model, and you could just say, split all future homes into these groups, and here's what we predict your value to be. But the power of computers now is that they can generate another tree based on a random subset of predictor variables and make new predictions based on other conditions. So here in tree 2, we've got, one thing that you could look at that splits the data is it a home or a condo? And so the homes tend to have higher prices, condos lower prices. The age of the home, an older home might have a lower value. A newer home might have a higher value. If it's really big, it might have a higher value. If it's pretty small, it could have a lower value. So you start to split out the data into all these different subsets based on the characteristics. Then you calculate these average values. Those are your predicted values. So from this model, you could say, from these 2 trees, let's just assume we only had 2 trees. We have a condo in an affluent area with 3 bedrooms, and the price is $380,000. Is this a good deal? And you might say, I don't know, maybe it looks okay. But you could use this model to tell you whether it's a good deal or not. So let's take it through these trees. Affluent area, yes. So then we go down this line with this arrow, more than 2 bedrooms, yes. Okay, our tree 1, our estimated value would be at $420,000. So if it's on sale for $380,000, hey, that's a pretty good deal. We should buy that home. But if we look over here at tree 2, we can see the first split, is it a house? No, it's a condo. Okay, does it have more than 4 bedrooms? No. So actually, the predicted value from tree 2 is 180,000. Wait a minute. Okay, put away your checkbook. This is not a good deal. This tree 2 indicates it's 180,000, while the sales price is 380,000. So we're 2 different models are sort of from the same training data are giving us different answers. Now, what the random forest does is it combines all the trees together and gives you the average estimated value. You take 420 plus 180, divide it by 2, your average estimated value is now 300,000. So that's the power of these computers. The machine learning builds a lot of trees, and you can average them all together. So 300,000 is the estimated value from these 2 trees. It's a better estimate. And through this, we've seen that the larger number of forests, the more estimates you can get much closer to a sort of an accurate estimate. And so again, I would say pass on this one. Look for maybe a home in that area. What does this have to do with rivers and stream gauges? So this is basically, we use the same method to try to predict stream flow. And in this case, the training data was watersheds with minimal human disturbance. So we're not trying to predict the actual flows yet. Laura's going to talk about that. We're trying to predict the unimpaired or natural flows. Given a certain amount of rainfall, how much flow should be in this river in any month of the year. And so we take select these watersheds. These are our reference watersheds, and they have to have a stream gauge. As I showed in an earlier slide, a subset of the rivers do have stream gauges. So we use that data to build these models. And we start to take key characteristics like the current monthly precipitation, the slope of the watershed, the temperature, the geology, maybe some annual precip numbers, some precipitation in previous months. And all of that can help you start to build these predictions of what the flow will be based on the observed data, the training data. And so that's kind of how these machine learning models work. For this project, we actually had the computer build 1,000 trees. So we have 1,000 sort of unique predictions of what the flow might be in every stream segment for every month of the year. And what we can do is we can take the estimated. So that's the average, just take the average of all the predictions and say that's our best guess of what flow would be. We can also look at sort of the spread of these predictions from each individual tree and take the 10th percentile. So not the lowest prediction, because that might just be sort of an outlier, but what is the 10th percentile and the 90th percentile? So now we have our best guess of what the flow would be in that month, and then the 10th and the 90th as to give us a range of values. So when you see P10 and P90 in the data set, that's what that refers to, is sort of it's not fully uncertainty, but it gives you sort of a range of what the models predict. And in places where it's harder to predict the flow, because there might be a large amount of groundwater influence or a really large watershed with a lot of variable inputs, you'll see a wider range on the P10 to P90. So that is building these models based on the reference gauges, the locations we have good data. And then to deploy the model or to infer what the flow is going to be, we apply that model to the input data, precipitation, temperature, and watershed characteristics for all the rivers in California. And so that's the stage where we get from where we have a little limited data set, then we expand out to basically fill in the data for all these gray streams, red and gray streams in this map. So I'm going to do a live demo next and get close to your chat button, chat entry here, because I'm going to ask for some audience participation. I figure it's always easier just to show people the data. So I'm going to go ahead and click on rivers.codefornature.org. This is a live website. Everyone is able to access it. And we have summarized some of the science behind this, the methods. There's a reference to a few peer-reviewed publications where we've written up the details. You can also download data in bulk or access it via API. So to get larger queries completed, we have some apps about drought flow data here, but the main place I typically go to is this mapping page. So here's your opportunity to participate. Name a river you're interested in California. Could be any river, but it has to be in California.
The Yuba.
Oh, okay. I heard the Yuba and I see the Salinas. We might be able to get to both of those. Talking is faster than typing. So, okay. So we've got, if I just type in Yuba, we've got some North Yuba. We have some gauges here. Feather River at Yuba City. That's not the one we want. I'll take a stream gauge here on the middle Yuba River below Jackson Meadows Dam. Okay. So this is higher in the watershed. But this search tool is a good way. You can actually put in latitude and longitude numbers if you want to. This is a good way to kind of quickly find a river you might be interested in. So here in this map, we have blue rivers indicate we have flow data, predicted flow for all the blue rivers. And then, so I'll just click on one of these from the middle Yuba. We have functional flow data. So this is predicted functional flows, also calculated with machine learning, but a slightly different method. So I'm going to skip over that. And then here's our sort of monthly data outputs. And this basically shows for the whole modeling period, we took wet years, dry years, and moderate years, and then just generated averages of what the predicted flow would be as a way to kind of summarize it. And so for a moderate year in May, this portion of the Yuba, our predicted natural flow, unimpaired flow, is 584 CFS. And so that's kind of across multiple years, what we'd expect. And then the shading here is the average of the P10s and the P90s. So that indicates kind of the range of modeling uncertainty associated with this. And so you can see this is probably a snowmelt dominated system where May tends to have the largest flows, and then it tapers off significantly till you get down to September. Predicted natural flow is only 12 CFS. So another thing you can do here is look at all of the data across time. So here we've got months as rows, we've got years as columns from 1950 to 2023. And then you can see the lighter colors means less flow. So the September, August, September tend to be the lower flow months, predicted flows. May tends to be the wettest month. And then you can hover over. So our last prediction was April 2023. We expected to have 316 CFS in April. And then we've also ingested some stream gauge data for these segments that are colored, either pink or purple. And so then you can start to look at, well, what is the actual flow? What's the observed flow? And here, this location, we only had observed flow from 1965 to 1987. So again, here's one of those stream gauges that went inactive, but at least it gives us some data. And the pink line indicates what was observed in this location. We're right downstream from a dam. So that's taking the peak, sort of slicing the peak off. You know, we're not getting those big flows in May. It comes a little bit later in June. And then interestingly, in one of the driest months, September, we're actually getting a ton of flow. So this is when the dam is releasing that stored water, probably for irrigation purposes, but 162 CFS when the natural flow should only be 11. So here's a typical kind of alteration we'll see in streams that have a large dam upstream, is that the peaks get moderated, and then the low flow gets inflated. So that's just some of the data you can get. You can add this stream to your queue. And then if you want to, you can certainly use these charts, but then if you want to download all of the data, P10s, the P90s, the observed data, we have monthly mean, max, median. You can just download a table and you get all of the raw data. And so this will give you the data for every year and every month, what the predicted flow is. And that's just opening up now. To get a sense of, in 1950, in January, here was our predicted minimum flow for that month. Okay, I'm getting low on time, so I'm going to swap back over to the slideshow. The last thing I want to talk about, just the uses. How are these data being used? We've heard of a variety of different uses throughout different water management scenarios. One thing we did was to take all of the data at those stream gauge locations and summarize the alteration. And so we wrote a paper back in 2017 that looked at how different the observed flows are from the predicted flows. And we saw both a lot of cases of depletion, and then also a lot of places, certain months of the year where the flows are inflated beyond what they should have been. Those are pretty interesting analysis. Another interesting use, the Department of Fish and Wildlife has used these data to help sort of provide guidelines or information about natural flows in various watershed scale criteria reports they've generated. And so here is one for the Ventura River. They picked a couple different sites and then reported out on what the monthly flows were, predicted natural flows for these sites for different types of years. So this is a way to kind of provide information about the natural flows and help that to inform water management in these locations. So just to close, I would say that machine learning, AI, data science can be really valuable in water management in California. Help us to fill the gaps. We still need stream gauges. We still need many more, but this can provide some additional data and build off the data we have. So it's really valuable. And I'll drop this link in the chat. After Laura talks, you can explore as much as you'd like. So thank you for listening, and I'll pass it over to Laura.
Great, thanks, Kirk. All right, it's course number 2 of Data for Lunch. I also don't have any food to offer except for data. So I'm going to pull my slides up as well. And you all see my screen. Let me go into slideshow mode here.
Yes, we can see it, Laura.
Okay, perfect. So as a way to frame kind of where our group fits in, I'm Laura Reed. I work for an organization company called Upstream Tech, and we've been partnering with the Nature Conservancy for 3 years now and counting to really address the same kinds of questions that Kirk has been asking for 18 years, which is how can we improve the accessibility and understanding of rivers for managing water across multiple use cases. And we come at this with a machine learning hydrologic science angle that is very similar. I'll talk about how we're kind of applying that to basically take the work that Kirk and Nature Conservancy and lots of others have done and go and try and estimate actual river flow that has alteration in it. So taking natural flows, which are a really, really important baseline, and going beyond that to try and understand how alteration has affected streams. And by way of kind of getting to that as an ultimate message, I want to just introduce like what we do at Upstream Tech and HydroForecast, this product that we're building, and kind of our mission. So I work for this small company, Upstream Tech, and we use data for good, basically, is our mission. This product that we have built, HydroForecast, is really aimed at water management. And some of the motivations for using AI and machine learning that are similar to what Kirk described is just the speed at which these models can advance and be deployed and scaled is just unlike anything that we've seen from traditional hydrologic models. I come from a process model background myself. I've worked on something called the National Water Model, which is this continental scale model. And even in that, where you've scaled across a continent, the speed at which you can actually advance the models and test out new experiments, new data, new variables is just with these ML type models, it's so fast, and it's going to really be important for how we can move the needle forward on predictions, especially in places where we don't have gauges and probably won't have gauges. So the other thing being, the underlying question here that we're helping with TNC and working with the state to help answer is, can you actually build one model that can have the generalized ability to predict altered stream flow in almost any type of basin? And it was funny, I was at a workshop last week where someone presented this kind of almost philosophical question. And he said, a software engineer with a machine learning background would say, absolutely, you can do that. And a hydrologist would say, there's no way you can do that. And so I think that's the tension that we're working in and the space that we're really excited to be in. Okay, so what is HydroForecast? Our bread and butter as a product here is operational stream flow forecasts. So we have this ML-driven model. We also constrain that based on hydrologic theory. I'll talk about that a little bit more. And we serve this to customers who need to know, how much CFS is coming into my reservoir, because I have to manage my water for floods, for energy, for lots of different applications. So we have a service that folks come and use our model for, and we work with groups to make that the most accurate model that we can. This is some of the list of the groups that use our model. So we've got folks from, like I said, energy utilities. We've got folks from water utilities, a couple local ones in California for sure, Army Corps of Engineers, et cetera. So growing, and we work on about 5 continents right now. We've got these different product horizons. So the focus today is on the historical analysis. So what can we say about reaches and basins that have never had a stream gauge, to basically be able to construct a stream flow record in those areas for using, asking questions about conservation. What was the baseline flow? What are the flows now? What's the gap between those? Where should we invest conservation? Where should we invest in gauges, et cetera? But so that's where we're focused today. We also have these forward-looking products that are more of a kind of an ongoing operational system. Okay, so really how it works. I really appreciated that analogy or metaphor, Kirk, that you used for buying a house and understanding house price. And so I won't go into like the machine learning piece, but just taking that kind of understanding or conceptual understanding of how the machine learning model works. We do a very similar thing. We don't use the random forest. We use something called a long short-term memory model, LSTM. So it's a neural network model that takes in information in a similar way where, okay, you're feeding it things that we know are important to hydrology. So that's anything from the weather. So all of the weather variables, things like that. That's previous gauge observations where we have them. And then we also feed our model with daily satellite images. So that is covering things like the vegetation index. So how green has the basin been, snow cover, snow depth. And those aren't forecasts. So those are like every day a satellite goes and takes a picture of the basin. And that actually helps this type of model learn what is snow, like what is soil moisture, because you're not writing down these physical equations that describe it. You're actually giving it data and asking it to understand and learn when to melt snow, when to accumulate soil moisture, et cetera. And the model learns that. We train our model. I'll show an image of the model we trained here over many, many, many basins. And so it can kind of leverage that data from different basins in a way that a typical model isn't able to. So here is our kind of our core, we call this our unimpaired or natural flow kind of workflow. Now, how do we get this model? If we want to have a goal, one model, how do we get it to learn alteration? So that's one of the key things we've been focusing on with the Nature Conservancy. And so we basically take this core model, we take our unimpaired flows model, and we give it more information. And then we train it on a large amount of basins. Some examples of these kind of enhanced basin characteristics or flow alteration patterns are things like how many dams are in the basin, what's the average of flow coming from a reservoir versus a stream, what's growing there, what's the population, like how many canals are there. So lots of different types of factors that maybe on their own wouldn't really give you that clear signal, but putting them together and the model seeing that over many different types of hydrology, it actually can learn these patterns. Okay, so that's kind of an overview of how this type of model works. And so to speak about like where we are right now and what we're planning on doing with this type of model, like I said, we've been building this for the application of altered flows, historical altered flows for the last couple of years. And our plan is we have a project with the Wildlife Conservation Board that we are developing basically a daily unimpaired and a daily actual flows record for every single stream reach in California. I should put an asterisk by that and say there are probably some stream reaches that will not have this available given if there's weird things within the data set, but that's really the goal. That's the scope and scale of what we're trying to build here. And we're going to work on that with just using a single model to do that, with part of the intent being like how, understanding how far you can stretch a model like this and what are the benefits of actually using a single model. So that's basically what we're trying to build here, and accompanying that data will be some evaluation. So we're going to take certain basins that our stakeholders in our technical advisory group are really familiar with and have lots and lots of data on that we won't use for training as a way to really understand the strengths of the model. So that's what we're up to for the next couple of years. And I'll kind of show you like where we're starting, what this model has been capable of as a way to say, where we're aiming to get to the end with this project. Okay, so last couple years, we've had all these phases. So this was like phase 3. We trained a continental scale model. We trained 2 actually. On the left is the unimpaired model, and on the right is the actual flows model. And basically what you're seeing there is if we take the map on the left, those are all of the sites that we use to train our unimpaired flows model. So it's about 500 sites, and that is based on loosely the CAMELS data set, which is a data set that has gone through and said, yes, these basins are unimpaired, meaning they don't have diversions, they don't have big alterations, dams, things like that. They don't have people opening, closing gates in a way that would redirect water unnaturally. So we trained our model, and you can see there's a big diversity of sites here. So we've got sites that are cold, sites that are flat, sites that are mountainous, and the colors there are just ecoregion. That was one of the ways that we slice and dice the data at the end. And so a couple of things about being able to train on this size of data set is that you may not need a very long record in each site, because data length can be somewhat debilitating if you have a discontinuous record, you only have a couple of years, et cetera. When you're training on many different sites, the model can not only use that data to supplement in areas where you don't have a lot of data, but it can actually help predict things that it hasn't ever seen before. So if you have a similar site that's somewhere else that receives, about the same rainfall, it's got the same soils, things like that, the model can actually learn and understand, okay, this site is somewhat similar, so I think I can make a similar prediction here. Same thing with the actual flows. So for the actual flows model, we used every single USGS site that was available that had data between the training period that we needed. And then we were able to actually say, okay, this model should be generally applicable across the entire US. Our test sites, so the ones that we hid from the model and said, you don't even know there's a gauge here. We're going to evaluate you on this model. These are the ones across California. So we had about 100 actual flow sites and 50 unimpaired flow sites. And we tried to we did like a random tessellation for a sample to pick sites in different locations and with different characteristics. So basically the idea being, where can you trust this model? Where does it do well? What are the limitations of it? Really trying to answer those questions by using these type of test sites. And I'll just show an example here. So I promise this was not intentional. This was completely fate and coincidence, but this is the Yuba River at Marysville. So I'll run through this here. Basically, the black line in that plot is the observation. So as we were just discussing, there are some dams on the Yuba River, and where you might have a natural flow cycle that has snow melt. So all the model's predictions are purple, and all the confidence bounds of the model are shown in those shades of orange. And our model is probabilistic, so it's putting those out with every time step. That would be the natural flow pattern. And so we don't actually know what the natural flow is because the gauge is recording the actual flow. But what we want is a model that can predict the actual flow. We want a model that can say, oh, I see you, I see what's happening in this basin, and I have learned to alter my natural flow pattern to meet that. So when we applied that actual flows model that I was just showing what we built, this is what we got. So you can see the model's mean prediction is in purple there. It's not perfect. It's not going to pick up on every single peak or fall, but it has dampened its signal in the spring to capture the fact that water is being stored there. And it's also kind of dampened out that second pulse that occurs a little bit later from a runoff that doesn't happen because we're still storing water. So this is one example of something that we've found from this model can be very useful when we give it this extra information, constrain it in a way that it's learning hydrology, and train it over many, many sites. I don't want to spend too much time on box plots and statistics, but I figure just to round out the conversation, we're looking at the model not only with hydrographs and qualitatively, but also with understanding of skill and being able to say, okay, this model performs better than if you had no information, because one of our main goals is to be able to add information. And so how do we do that and then verify that this model can be used, and how can it be used? So I'll just show this. This is the Nash Sutcliffe efficiency. It's a skill metric. A perfect score is 1. If you're below 0, you might as well just use your average observed flow for your predictor. Of course, in these conditions where we don't have any observed flow, you could argue that an NSE of 0 is still pretty good because you don't even have anything. But I want to focus in on this middle plot here, which is basically we took all the high flow. So we wanted to ask the question, does this model do well in the base flow, which is really important for ecology and understanding if the stream's going to go dry, if fish have enough water to spawn, and does it do well in high flows, which are also really important for ecological conditions. And where we want the model to be is at 0, because we don't want we want the model to be at 1. Actually, that would be a perfect Nash Sutcliffe, is it be at 1. And you can see the median there is right around 0. And so for the base flow, and you can say, well, why is that? Like, what could be happening in the base flow? And so if you just take the statistics for what they are, we still need to dig into that picture and ask why we're getting some of these values. And one case of that, if we dig in, is understanding what's going into the model. So the top plot there is showing the observed values during our validation period. And I don't know if you can see, there's just the one blip. So there's only one time that the flow wasn't 0, because if you look on that y-axis, basically the CFS is 0.02 at the top, and the rest of the time there was no flow. And so one of the challenges I just want to highlight with this type of approach, where you're trying to build one big model, you're trying to understand its value on a large scale, is that we still actually need some humans and expertise and folks to be helping to look through the data, clean it, make sure how we're evaluating our models is in line with the use cases that we want to use it for. Because you can't just like say you built this great ML model or even hydrologic model and then go produce results and trust in and understand them from that point of view. So one of the things with this project is we have a great technical advisory committee that is helping us to pick basins and places that don't give the model an advantage at all, but that we can really truly understand at its core level what it's doing and make sure that we're producing data that can be useful and understood. So thank you for listening, and I will stop there.
Well, that was fantastic. Thank you so much. Really appreciate the conversation. I think Nick is going to kick us off on questions and the like.
Yeah, thank you both. The first question I'll go ahead and read is from Jeremy Gata. Did you all consider starting seed effects in your analysis? In other words, do multiple models each with 1,000 trees? So this question I think was directed to Kirk.
Sure. I will, in full disclosure, we actually worked with some researchers at USGS to do the initial round of random forest modeling. And so I don't know how much they looked at starting seed effects in the analysis. I've reviewed their code, and in the paper we wrote up, we don't mention that. So I don't know how much we did consider that. My understanding is that during the sort of the training and building the models, we didn't sort of set any one particular seed to fix the results, and we would be kind of randomly choosing training sets and testing sets as you go. And then once you sort of lock in your model, you want to set that seed so that you can recreate it. But that would be a better question for Darren and at USGS, so I can pass that on. And then the second part of your question was multiple models, each with 1,000 trees. That is true. We have something like 40 different models, because we have one model per ecoregion, per month of the year, and then per variable. And so there's 3 ecoregions we looked at, and then 12 months, and then we have monthly mins, monthly maxes, and means. So yeah, that adds up to a lot of different models, and each of them had 1,000 trees.
Awesome. Thank you, Kirk. This is a question from Hannah von Hulbert. And I think it's directed toward you, Kirk, but would actually be interested to hear Laura's response as well. And so the first question is there data on shallow groundwater data within the natural flows database? Or will those measurements be in TNC's integrated I think it's groundwater dependent ecosystem database? And so, yeah, I'd love to hear your response, Kirk, but then Laura, I don't know if this is something that you've integrated into some of the training some of the data that you fed into your model.
Yeah, this is a great, it's kind of a merging of my two worlds too, because some of my time I support our Healthy Rivers team, and some of my time I support our groundwater team. And so I've done a lot of work on groundwater dependent ecosystems or GDEs. The models don't output information on groundwater. So the natural flows database doesn't have any output on groundwater depths or shallow groundwater data. We have some variables that can be used to sort of think about groundwater. So there are some variables about the watershed that include sort of the depth of unconsolidated sediments, and sort of there might be an indicator of groundwater basin. What I've found is that in places where there's a lot of groundwater interaction, the models just have a wide range of predictions. They don't, just because the geology can be so complex in some of these ecosystems, and there isn't a lot of training data for all of the different systems. I bet Laura's model with that broader data set probably actually does a better job on groundwater interactions. But we did do an analysis, I'll just share my screen real quick, on looking at groundwater dependent ecosystems and trying to estimate shallow groundwater depth. And this is called SAGE. I'll put the link in the chat as well. And we have a paper out. So this might be what some of this question's about is this other tool, which is another machine learning effort to sort of estimate shallow groundwater based on remote sensing data from groundwater dependent ecosystems. So we do have another tool and another data set that helps predict that. So I'll put that link in the chat. But Laura, any comments on groundwater?
Yeah, it's a great question. And we do have some variables in the model that relate to soil. And I was just looking at the complete list, which I'm happy to share out of all the input variables that we put in that are about permeability and the types of content. And then also we can add in more variables. We don't have anything specific right now on like depth of groundwater or water table movement or using even gauges where we would have information about that. But that could be something that we definitely play with a little bit more.
Great, thank you. Another question from Denise Wesley. What do you suspect is the reason for the lower score in the xeric ecoregion?
Great question. Yeah, the xeric. So one of the things we realize about the ecoregions is they are helpful because they divide the data up. They're also a little bit broad. So xeric included, I can throw the map back up here, but it included sites not only in the south, but all along the coast. And one of the things, I'm just trying to pull my screen back up here. One of the things that we noticed is that a lot of the xeric here are in pink. And these sites down here at the very bottom on the coast, those are some of the intermittent flow sites that I was showing an example here from, where you may not have an event at all in the validation period, or you may have one, or you may have two, and the flow may only go up to like 1 CFS. And so when you're calculating error on a low flow or just one event, the actual bias is not that bad, but statistically wise or numerically wise, where that lands in the Nash-Sutcliffe efficiency score, it's going to basically inflate that bias in a way that makes it seem really off. I think to your bigger point, the question is how can we take what we've done and like as we're dividing and slicing and dicing the results, like how can we make sure that we're understanding that better? And that's what I'm hoping that we can do with this technical advisory committee and really trying to dig into basins where we know that we can trust the observations and trust that the data are, these are good sites to evaluate on.
Awesome. Thank you both. And I see Tim has his hand up.
Yeah, thank you. I work with Creeklands Conservation. We're on the central coast of California. And I always get excited about these tools because we have a lot of ungauged watersheds and they have a lot of variable hydrology. And what we try to do is a lot of stream flow enhancement projects, bump up the flow in the dry season to increase habitat. And we've worked with Kirk and his team to test out that tool a bit for some of our key watersheds. But I'm curious, one thing we like to do is try to figure out how we're going to prioritize our watersheds and where we think we could have a impact with the type of projects we do. What's the potential for using these models to like pick a desired future condition and then like back out the variables that we could influence to increase stream flow, for example? And sorry, that's for either person.
Okay. Yeah, Laura, I'd love to hear your thoughts on kind of the key variables and if we've gotten to that stage of sort of what makes a stream more altered.
Well, yeah, I guess one thought is one of the things we've talked about with basically having this altered flow record and the natural flow record is like, what is the difference in that gap? Like, I think that's what Kirk and Julie from the TNC team is envisioning is like, okay, the watersheds that have the biggest gap between what's natural and what is actually happening on the ground could be like the order of priority that you may want to go and figure out like a policy or a way to reduce that gap between altered and natural. So I think that's like high level, one of the things where one of the use cases we're hypothesizing could come out of this work. I think for variables, so just to ask you a question back, are you saying like, okay, I want to be able to enhance my stream flow or change the pattern or something to in these areas, like what should I actually go do? Is it plant more trees or things like that? Is that what you're saying?
Yeah, something like that where, you could say, let's hold the soil type constant because we're not going to change that. But let's see if modifying the way this reservoir is operated would have an actual impact that we could measure.
Yeah, definitely. I think there's ways where we could even take similarity as an approach, as in like, okay, I have because we're making this model that covers many, many basins. I could see a path where you'd try and find basically a place that has higher flow, but with similar conditions, which if we like went into the model, we could tell like, okay, this basin has 7 dams, or it has this type of soil and like, but has a different flow pattern, and like see how you could see what's different in a way that could help you understand like how to get to that other state. I don't know. That's one idea. Kirk, what do you think?
Yeah, I love this question because I haven't really thought about it this way, but basically, as we're generating these altered flow models, we can start to look at which variables were important in sort of predicting something that was different in areas that where it's different than natural, and then start to examine those variables. And if the main thing is something we can't control, then that's good to know. But if some of the key variables are things we can control, like number of dams and sort of the size of the dams, that might indicate, okay, dam reoperation is a key strategy. So yeah, I hadn't thought about it that way, but I think we could do some pretty interesting analyses. Yeah, thanks, Tim.
Thank you.
Love this discussion, and I'm going to pause us here. We're 2 minutes before 1. As I mentioned before, well, first of all, I want to say a huge thank you to Kirk and Laura for presenting here today, teeing up this wonderful discussion and really orienting us to the work that they're both doing currently, but also looking to do moving forward. So huge thank you to you both. They have both said that they will stay on till as late as 1:30. For those of you who do have the time to do so and have not had your questions answered yet, please consider staying on, and we'll try to get to those as well as other questions that will come up, I'm sure. So with that, thank you all for being here. I hope you enjoyed sort of the more formal portion of our data for lunch. But if you have additional questions, please do stay on. All right. And I see that, so actually I want to go to this question from Shiheng, who asks, for the unimpaired flow, is it forecast? And if so, what is the lead time? And I think, Laura, you touched on this, but it'd be great if you could expand a little.
Oh yeah, sorry if that was a little confusing. So the thing we're doing here with TNC is it's not a forecast, it's more of a hindcast, or it's a reanalysis is what we would call it, from 2000 to 2022. And so in that case, there's no lead time, there's no forecast, it's just a daily, imagine like just a reconstruction of a stream flow record. But for the forecasts where those are operational, looking out into the future, we have like a short-term forecast that goes 10 days and then a seasonal forecast that goes 90 days.
And Laura, for those forecasts, are you building that on a unimpaired model, or is that an impaired actual flows model?
It depends on like the basin and region, but we can incorporate like actual information into that model. Yep.
Cool. And that tends to be done at specific sites, right? It's not something that we're going to do for all. We're not going to run forecasts for all rivers in California. It's something more if you have a particular site you're interested in.
That's right.
Yeah.
That's exactly right.
Exciting to hear there. Okay. I see Gus has his hand up.
Yeah, this is actually for either Kirk or Laura. Really interesting presentation. I am hopeful that these tools will work in the future. Still slightly cautious about them working because California is a huge state and there's a lot of variables that go in there. I guess my question is slightly more philosophical in the sense that, a lot of machine learning is, well, we don't really know the mechanisms of it, so let's just throw data at the problem and let the computer sort it out. The problem is that, which is, the reason why you're doing this to begin with, is that there is a significant lack of data in a lot of these watersheds. So do you see, I guess it's a two-part question. One is there a catch-22 that you have where you're trying to solve the problem by throwing data at it in areas that already don't have very much data to begin with? And then second, is there inherent risk in developing tools like this where, say, USGS goes, well, why do we need to install a stream gauge? We have this tool that already predicts it, even though we don't know if it's predicting it very well. So sorry if that was a little bit long-winded, but just curious what your thoughts on that are.
Yeah, maybe I'll take the first swing. So I think with the unimpaired flows or sort of natural flows, I think we do have these kind of precipitation models. They're not perfect. We do have a lot of the sort of the input data that you would need in order to predict flows. And so I think from a philosophical perspective, that information and a lot of this analysis has really just been to take these data sets and accumulate the predicted or the measured rainfall down to these different stream segments. So you have to basically calculate what's the accumulated precipitation at every stream reach. And so those data were out there, but through this process, we've been sort of doing that on a regular basis. And I think that the value of the machine learning is actually forcing us to do these analytic steps and sort of summarize the data in the right way. So if we're kind of generating new data summaries and applying it. So I feel less concerned about the unimpaired flows. I think for impaired flows or actual flows, we're really grappling with some of those questions. And a good example is density of canals in a river. And I think we all know that just having the count of canals intersecting with a river is not really the best indicator of what's going on. Is that canal adding water to that river, or is it taking water away? So is it a positive to the flow or a negative? And in a lot of cases, we don't have that information at this scale. Or you could have 10 canals that are all taking very small amount of water from the river, or one canal that's taking all of the flow from the river, and so just the number or density of canals is not, that's a case where we have some data, but not enough to really predict flows. And so there is where, we, as Laura was mentioning, we need the human in the loop. We need sort of interpretation of some of these results before making really big decisions about them. So I still think that having, again, we're putting these data out there and then looking for that kind of feedback and review. So was that both parts of your question, Gerald?
Yeah, that's fine. It was, like I said,
Okay,
it was a little long-winded, but I guess the second one was, do you potentially see a risk of having tools like this and then, not actually going out and physically collecting the data because somebody can just point at your tool and say, yeah, we've already got an estimate here. Why do we need to actually go out and collect data?
Yeah,
and this is coming from a modeler who we should build models for everything.
Yeah. I see that. Yeah, that could potentially be a risk if but it would be a good problem to have if the models were so good that people said, hey, you don't really need a stream gauge. Look how great this model is. I'd be really excited, but there's a heavy level of skepticism. And so, I think we still see the value of these gauges, and actually, because you need so much data in order to train these models, one of the main outcomes from this effort is we need more stream gauges, especially in reference sites, especially in the larger rivers, so and then the more data we have, the better we can train the model and the better we can test it. So I actually see the modeling encourages more stream gauges. And I hope someday that we get to the point where stream gauges are just obsolete, old technology. But we're not there yet, for sure. Laura,
Excellent, thank you.
Any philosophical thoughts on that?
Sure. I know we have other questions, but I'd love to just hop in, and I really appreciate that question. I think that's exactly the thing we want to address with as the pendulum or things shift to include more machine learning and hydrology. I just think it's really important to hear those and acknowledge the skepticism. That's really important. And I hear that you're coming from a modeling background. So I think my response is in backwards order would be the same as Kirk, where the more gauges we have, actually, the better the models are going to be. And we never see a replacement between the thing that we're building and having more stream gauges. I think what we're sensing is there will be less investment in on the ground stream gauges as they have been. And so how can we actually use the data that we have in a different way to where we're not building a basin model for every single basin where we have a gauge? We're actually leveraging all the USGS gauges or all the CDEC and all of it together to make the best use of that data so that we can build better models. And then I think to your first question about just like building a model that's memorizing patterns and not understanding anything, totally agree with you there. If you Google or search some of the latest academic research on what we call our approach is theory-guided machine learning, which is to say you're constraining the model in a way that only things that are physically possible can result. And the way that you do that is training it on many, many, many basins so that it's understanding soil moisture and infiltration and snow melt in a way that actually a single physical hydrologic model could never do, because it also has parameters that are not measurable and things that are assumptions that are not going to hold true if you go somewhere else. Then I think we're trying to basically be able to take advantage of the fact that computing has advanced and these types of models have advanced, and the LSTM particularly is just well suited for time series predictions. And I think more and more people are finding that. I hear that when I go to academic conferences and things like that. And so we're trying to be like helping to bring that more into the forefront, not at all abandoning like having to figure out like physically why that's possible, but just seeing the advantages of that approach. And I think to Kirk's point on the canal density, totally agree. You don't know like, why is this variable important on its own? But if you're looking at like hundreds of basins that have different types of canals, and you're putting that together with dams, and you're putting that together with soils, and you're putting that together with population, it's like we as humans maybe can't figure out exactly how that's working, but there is some connection there between that and flow. And so like, let's have the models like identify that and then us go figure it out versus having to like figure that out on our own and then parameterize a model to capture that. I think that's the thing we're trying to work on. So thanks for the question.
Well, thank you. Great presentation.
Great question. I love this portion of the discussion because we get these questions that really in time to allow us to sort of explore them in more detail. So thanks for that, Gus. I see Jeremy and Bhavin waiting patiently, but I also don't want to lose this question that Hannah dropped into the chat, which is where does the soil data come from as input to the model? And then what soil characteristics are used as inputs, such as available water holding capacity or other characteristics. And then she also asks about uploading or updating that data in a fully calibrated model. So I think that's a question for you, Laura, but Hannah, please feel free to jump in and flesh that question out if I misrepresented anything. And I think she's still on here, but maybe not.
Yeah, I could follow up with her. Are you still here, Hannah? Or-
No, I think she did drop off, Laura.
Okay. Cool. Yeah, let's hit some folks with their hands up.
Okay, let's do it. Jeremy.
Yes, sorry. Fun stuff, good talk. One of the things that I've noticed so much about machine learning, especially in ecology, is that we spend a lot of time focused on the prediction part. But these models, because of their nonlinear, non-parametric nature, at least the random forest-based ones, also can really pull out patterns that we've hypothesized, but actually haven't proved empirically. And so I was wondering, have you explored your SHAP values and, you know, explored other aspects of the machine learning models and discovered any interesting patterns, especially for the nationwide data set? And thank you.
I would say no. That's my short answer. Can you expand a bit? You mentioned SHAP values. I'm not familiar with that term.
SHAP, it stands for Shapely Additive Explanations. And my colleague explained this to me the best. He said, it tells you on any given day why the model made the decision it made, what was it thinking? And so for every single prediction, you can essentially, so like, let's say your variables are some snow metric and something about ground cover or something. And it will tell you which one of those metrics contributed positively or negatively towards the decision and the relative magnitude. So, you know, you think about variable importance, and that tells you overall, you know, throughout the entire data set, what were the variables that were included in the most trees. But the SHAP values tell you on a daily time step what the model was thinking.
Okay, I'll have to kick that to Laura because we haven't done that, at least on the monthly models.
Yeah, can you see my screen? I think I tried to put up some example. Yeah, great question. So we have done that. There's an approach. So we don't use the random forest. We have the LSTM, and there's an approach called integrated gradient where you can do the same. You can do a similar thing, and you can say, okay, on April 1st, when you went and made this prediction, what were you paying attention to, either in a positive direction, so like if there was snow, or in a negative direction, like if there was a really high temperature, and how important was that in the prediction of the next 3 months or 2 months of stream flow? And we do that in our models, especially when we notice that something is not in our prediction models that we run operationally, especially if we're like seeing the prediction, you know, the flows going up. We don't have any snow on the ground. There's no rain in the forecast. You know, what's happening? And so we do have a way to do that, and we have a set of tools. We have not done that in a systematic way with the reanalysis predictions that we've worked with Kirk's team, but I think there's a lot of interest in that, and we've talked about integrating that into our next phase. So yes, good point.
Yeah, just to add a little note, I definitely would encourage that. We're wrapping up a model, and we've learned a ton just by doing that. And the other really interesting thing that's come out of it is, you know, as scientists, we have certain ideas like, you know, high flow is good for this and bad for that. But using these models, you can actually find tipping points by looking at those values. So yeah, definitely dig into that, and I look forward to seeing what you all discover. Thank you.
Excellent. Well, thank you. And I see Bhavin has his hand up.
Hi, my name is Bhavin. I'm a data scientist with GHD. So I understand a bit of data. I might not be an expert like how Kirk and Laura are, but thank you for presenting. That was really good insight. I've been exploring the data sets from DWR as well to model the groundwater levels, all the 6 sustainability indicators. And my basic question with just sticking with one particular model is, what's the reasoning behind, let's say LSTM has I like to do the univariate analysis first and then understand what are those variables that have more of a predictive power. And then I've gone the traditional route right through my academic and now out here at GHD. So I'm wondering, does LSTM and random forest, when you go along with a particular model, what's your approach in making sure that the variables that you use have a high predictive power and you're not introducing noise or some bias? And that has always been a question for me, especially when you predicted for the whole even county.
Yeah, I can take a swing at that. So when the USGS team was sort of training these initial random forest models, they built in a sort of iterative process to randomly subset the input variables, because they have, a long list, I think 400 input variables, and randomly select 20, randomly select, and then generate models and see which ones had the best performance. And so they did that several times, and then picked out the variables that showed up in multiple models that had the best performance. And so there's a process they went through to kind of subset variables in order to pick the ones, and they use the machine learning tool set in order to do that. So that's one method, and we've been going through that kind of that same process. Or can we replicate this method that they generated now that we have newer updated data to add? So we have some code to sort of do that similar process, but that's the kind of way you basically look at these variables always show up as having high variable importance scores, and thus from across multiple models. So we'll put them in the final model. So that was how we approached that. Laura, how about you? Variable selection?
Yeah, I mean, I think that's the theory guided part of the theory guided machine learning, is that you want to have the simplest model that doesn't have, like, the fewer number of variables, the better, because then you don't have as many parameters and hyperparameters and things like that. So we try and approach that from the bottom, adding the things that we know govern hydrology, snow, precipitation, temperature, soil information, things like that. And then understanding the errors and where those errors are occurring as a way to guide, okay, what are we missing, or what should we be tweaking that can help us represent the hydrology better.
Okay, got it. Hey, thank you. You guys have a lot of patience to do this. Hats off to you guys. Thank you for sharing.
Thanks for listening.
Yeah, thank you.
Thank you. And I see Tim has his hand up.
Yeah, I was just wondering if, so when I look at hydrographs, I like to look at base flow a lot and look at, the fluctuations throughout the day, and sometimes try to interpret maybe what's causing that. Was that a pumping event? Was that, a lot of evapotranspiration? Can these models look at the shape of a hydrograph, either of like an input or maybe its own prediction, and draw some conclusions about the fit of the prediction? Just like, yes, that looks like a normal pattern, or no, that looks like an unusual pattern.
So you're looking at, and this would be in impaired systems, right? This is where you're expecting there's diversions affecting the flow.
That'd be one example. Like, in some base flows, you've got the high and the low, the diurnal cycle. And let's say your model output like a flip of that. Would it be able to see like, oh, I predicted this wrong. It should be higher in the morning and lower in the afternoon. Is that valuable even? Is it a good question too?
Yeah. I mean, I think we've only modeled at the daily time step. I don't think we've done any sub-daily yet. So we may not have those patterns within the pattern, right? We're kind of like we have the broader pattern, but I like the idea of kind of investigating the hydrograph to sort of see like what could be causing, what's the fingerprint of the alteration here? Is it you have a natural diurnal flow or not a natural diurnal flow, or do you expect it to go up and it's really going down? Those are some cool ways to explore.
Yeah, it doesn't necessarily have to be the hourly time step, but that's what came to mind.
Yeah, I was thinking about that for our operational models, we have an hourly model that goes out 10 days. So we can capture that intraday variability, which can be really important. And I guess I would say, yes, our models could capture that non-natural variability if it had data that it was like gauge data that was also reflecting that non-natural pattern. Because then when we make those models, we incorporate upstream gauges in a way that would reflect that actual behavior as it propagates downstream.
But Tim, I like this idea too, which is a slightly different question. It's kind of like mostly what we've been trying to answer is in a place where you don't have a gauge, how do you generate data to help you inform your decisions? But here your question is kind of like in the location you do have a gauge, how can you investigate these harmonics and frequencies and various patterns you see in the data to start to point to insights that you may not have data about. Like you may not know exactly who's diverting when and where, but you can see these patterns coming up, and it would help sort of highlight, okay, that's likely a pump that turns on every 4th day, or that's likely a dam release pattern or something like that. That would be an interesting tool set for data analysis.
Exactly. Yeah, thanks.
Yeah, we'll be busy for a while.
In demand. We have a question from, and apologies if I'm mispronouncing this, but Renuma in the chat that asks, how is the LSTM model? How is it performing at sites where it's not trained?
Yeah, great question. In the plots I was showing before, those were sites that the model had never seen for training. I had never seen the observations until we just put them on later for visual purposes and for computing metrics. So all those Nash-Sut cliffs, which had about a median of like 0.55 across the 100 sites, all those sites were only for evaluation. So it depends on the ecoregion or the area, but generally those models are, I guess I would loosely say, providing more value that they exist and can be used than if they didn't exist and you didn't have any data at all.
Great, thanks, Laura. And I know we're coming close to time, but I wanted to ask a question about, particularly given the consortium's mission of making sure that we have high quality, accessible data to inform water management decisions. How will the data from this work be made available? Will they be publicly available? Kirk, you sort of walked us through some of that, but maybe this is a question then for Laura of how do you intend to make these data public, or is that a goal?
Yeah, for sure. The work that we're doing with the Nature Conservancy and with the California Wildlife Conservation Board, that's all public. And so I think the goal is to integrate that into some of TNC's platforms and tools, and also to make the data publicly available, just to take either from our API or downloadable from a CSV file.
That's awesome.
I think our senior software engineer, I think his head's going to explode when he gets a sense of all the data that Laura is going to be shipping to us in these massive crates of hard drives. Yeah, because right now we're hosting the the monthly predictions. And so to kind of step that up to the daily for unimpaired and actual, it's going to be a pretty big increase in the volume of data. And so we're going to have to think a little bit about how do we serve that in a way that's sort of responsive and accessible, easily slice it based on what you need, but also provide access to the full range of data. So yeah, I think our engineer is going to have a little bit of work ahead of him on that, but it's a good kind of work. And in terms of timeline, Laura, we're kind of kicking off this modeling effort right now. We have several years. I think it goes through 2025, and so sometime before 3rd of October 2025 is when we're going to get these data analyzed, put up on the website. So that's the daily actual and unimpaired flow data. But to keep you busy until then, the monthly flows are up there already, along with these functional flows.
That's really awesome. Very exciting to see that all roll out, I think. So have a lot of folks who will be interested. Okay, I have one final question. We've talked a little bit about the importance of stream gauge data in really helping to train this, ensure that we have model accuracy and the like, but also that part of the motivation is just knowing that maintaining these networks long-term is expensive. We've seen them become active and then be inactivated and the like. And so question for both of you is, how do you see this work informing sort of strategic stream gauge placement? And if so, like, how would you consider that if we think about just limiting the amount that we invest, but doing so in a really strategic manner?
Yeah, I can take the first shot at that. Some work by Ted Grantham. He's another kind of big pillar in this machine learning for river flow space. He identified the types of watersheds where we don't have representative stream gauges now. And so, these, especially when we're talking about unimpaired flows or natural flows, these are places that are unimpaired and have certain characteristics about the flow and the geology and the location that the current stream network doesn't represent. And so it's kind of a different way to think about things. We typically say, well, we need a stream gauge where you have a dam or where you have a lot of people relying on a river. So this is sort of flipping it on its head, is where we need stream gauges in places unlike what we have now. And so he has some great mapping work that sort of pops it out into the corners of the state and get more gauges in the Modoc and in the Amargosa and places like that. But he's done sort of the most work on that. So I think that's one way to think about it. And then for actual flows, I don't know, Laura, if we have a lot more gauged on impaired streams because there's a lot more impaired streams, but have you thought about the representativeness of the gauge network?
Yeah, I think we've talked about this some with our project group of, you have gauges that are representing big streams, they're put at big diversions, or you have a certain almost demographic of stream that's represented by gauges, and then you have a demographic that's left out. And so how do you kind of deal with that when you're training and evaluating models? And I think that's one thing that we're going to have to grapple with when we're building the actual flows model, is not having some gauges where we know there's altered flows and we don't have any information, and that's where we're trying to leverage that continental scale model to give us information in a way that wouldn't be there if we were just doing basin by basin.
Well, awesome. Thank you both. Really appreciate you being here. And thank you all for sticking around for a wonderful discussion after. More to come on this. It sounds like we need an update in a couple of years. So awesome. All right.
No problem. Well, thank you so
you.
much, Tara, for hosting and for the great discussion. I've learned and it's expanded my thoughts on this. So I'm really glad to have done this. And yeah, we'll also want to get your feedback on data availability as well and how we can improve that.
Excellent. We'd be more than happy to bring people together on that.
Awesome.